You ever stop and think about the physics of, I don't know, a spinning top, a turning wheel, or even a planet whizzing through space? It turns out there's this kind of hidden language that governs everything that spins, and today we are going to learn it. Let's dive right into the secrets of rotational motion.
Okay, to get our heads around this, let's start with something familiar, a spinning CD. If you really look at it, a spot on the outer edge looks like it's just blazing around, right? But then a spot right near the center label, it's barely crawling. So how is that even possible? They're both stuck to the same solid disk. That's the puzzle we're going to solve today.
So to crack this CD mystery, we need to get the right tools for the job. And that means we need to start looking at circles and rotation the way a physicist would. Let's find a better way to measure a simple turn.
All right, the first big idea is something called the rotation angle. Now, in physics, it's not just about, 360 degrees. It's actually defined as the arc length traveled, so the distance along the curved edge, divided by the circle's radius. I know that probably sounds a little abstract right now, but trust me, it is an incredibly powerful way to describe any kind of spin.
Look, we're all used to degrees, right? 360 of them in a full circle. It's what we learn in school. But physicists, well, they prefer a unit called the radian. And you might be asking, why bother? Well, it's because radians are built directly from the circle's own guts. It's radius. And that simple fact makes all the math that comes next so much cleaner.
So here it is. This is the big one. The one conversion you really need to know. One full trip around a circle, what we call 360 degrees, is exactly 2 pi. That's 2 pi radians. Seriously, if you only remember one thing about radians, make it this. A full circle is 2 pi. That means a half circle is just pi. This is the key that unlocks everything else.
But what even is 1 radian? Okay, imagine this. You take the radius of a circle, that line from the center to the edge. Now pick it up and lay that exact same length down on the edge, on the curve. The angle that piece of arc makes from the center, that is 1 radian. See? It's not some random number like 360. It's a measurement that's born from the circle itself. It's natural.
Okay, great. So we figured out how to measure the amount of rotation. The next logical question is, well, how fast is it rotating? It's time to talk about the speed of the spin.
So physicists have a fancy name for this, of course. They call it angular velocity, and they use the Greek letter omega to write it down. But don't let the name intimidate you. It's really just the rotation angle, those radians we just talked about, divided by time. Honestly, the easiest way to think about it is just spin speed. That's it. How many radians are you spinning through every single second?
Let's make an analogy here. We all get linear velocity, right? That's just how fast you're going in a straight line, meters per second, miles per hour. Well, angular velocity is the exact same idea, just for things that are spinning. Instead of distance over time, it's angle over time. It's just the circle version of speed.
Okay, we've got our new tools. We have the rotation angle in radians, and we have our spin speed, or angular velocity. Now it's time to put it all together and finally solve that mystery of the spinning CD.
Now listen up, because this is the absolute key to the whole thing. The CD is one solid, rigid object. That means every single point on it, whether it's near the middle or way out on the edge, has to rotate through the exact same angle in the exact same amount of time. And what does that mean? It means the angular velocity, our spin speed, is completely identical for every single part of that CD.
Okay, so if the spin speed is the same for every point on the CD, then something else has to be different, right? Something has to explain why the edge seems to be moving so much faster, and that something is the radius. It's just how far each point is from the center of rotation. And this brings us to this beautiful, super simple equation that ties everything together. It says that the linear speed, v, of any point on that spinning disk is equal to its distance from the center, r, times the angular speed, omega. That's it! This little formula is the bridge that connects the straight line world with the spinning world.
So let's just unpack what that formula is telling us. It says that linear speed, v, is directly proportional to the radius, r. So think about it. We already know the spin speed, omega, is the same for the whole CD. That means if you have a point with a bigger radius, like way out on the edge, it must have a faster linear speed than a point with a tiny radius near the center. It's not magic, it's just what the math demands.
And boom, mystery solved. The edge isn't spinning faster in terms of angles per second. The angular velocity is the same everywhere. The real difference is that the point on the edge has to travel a way bigger circle in the exact same amount of time as the point near the center. And the only way to cover that much more distance is to move faster. Its linear speed has to be higher.
All right, that was a great little conceptual puzzle, but let's see how this stuff actually works out in the real world. We can use this exact same physics to figure out something super practical, like how fast is a car's tire actually spinning?
Okay, let's set up the problem. Our goal is to find the tire's angular velocity, that omega or spin speed. What do we know? Well, we know the car itself is moving at 15 meters per second. That's our linear velocity, v. And we know the tire's radius is about 0.3 meters. All we have to do is take our magic formula and just rearrange it a little to solve for omega. Then we just plug in the numbers.
And what do we get? We get 50 radians per second. So, what on earth does that mean? It means for every single second that car is driving down the road, its tires are rotating through an angle of 50 radians. To put that in perspective, that's almost 8 complete spins. Every single second. That's pretty fast.
And really, what this calculation proves is just how tightly a car's forward speed is locked to the spin of its wheels. You can't have one without the other. The faster the car goes in a straight line, the faster its wheels have to spin. They're permanently connected by that beautifully simple relationship V equals R omega.
Okay, let's just do a quick recap of the big takeaways here. Number 1, in physics, the best way to measure rotation is with radians, and just remember, 2 pi is 1 full trip around. Number 2, don't get scared by angular velocity. It's really just a fancy way of saying spin speed. And number 3, the magic formula, V equals R omega, shows us exactly why speed on a spinning object depends on how far you are from the center. The farther out you go, the faster you move. And that's our deep dive into the language of spin. So, now that you've got this new way of seeing things, I'll just leave you with this question. The next time you see a merry-go-round, or a spinning fan, or heck, even look up at the planets, what are you going to see differently? I hope it gives you a whole new perspective. Thanks for tuning in.